Okay, so we are going to talk about carboxylic acids today, just introducing the functional group, really. And next week, we'll focus on the reactions that involve carboxylic acids. And I guess you could say that we, in a sense, save the best for last because you do see these a lot in nature. They are very important compounds, type of compounds in nature. I guess, first of all, I should say that in the condensed structural formulas, okay, there's two ways to write it. We've seen before how the carboxylic acid is often written as COOH, okay? But it can also be written with the subscript 2 on the oxygen, just beware. And as you can see to the right here, this is the general formula for a carboxylic acid. You got the carbonyl group. We've seen that with the aldehydes and ketones already. And in this case, one side is attached to an OH. All right, that's the unique structural part of a carboxylic acid. Okay, and so again, one of the reasons why they are considered to be a pretty important type of compound is because they're abundant in nature. So for example, in the diagram you don't have in your handout, it's just really to kind of show you what I'm talking about, to hopefully jog your memory about some biology course, that you see carboxylic acids show up a lot as intermediates and products of metabolism in a lot of different biological reactions. So the one I've got for you here as an example is glycolysis. So glucose breaks down into two carboxylic acids. These don't have the hydrogens on them. The O minus, you just throw a hydrogen on there, you got carboxylic acids. But that's one example. There are many. And then here's another one, amino acids. They've got two functional groups. They got the amine functional group, but they also have the carboxylic acid functional group. And we know that they're important because those are the building blocks of proteins. So they're abundant in nature. But in other types of chemistry, they're also very important because they will many times serve as starting material. Okay, so they're commonly used as the starting point to synthesize other functional groups, which again, we'll get into that next week. All right, so let's learn a little bit about carboxylic acids today. So first of all, as it has been the pattern, we're going to talk first about naming. And similar to the naming rules for the other functional groups, we're just going to change the suffix. We're going to take the E off of the alkane parent name. We're going to change that suffix to an oic acid. So the terminal E of the alkane is replaced with oic acid. And just like aldehydes, when you have a carboxylic acid, you know where carbon number 1 is because that's the carbon that has the carbonyl and the OH off of it that becomes carbon 1. So the carbon atom in the COOH becomes carbon 1, with one important exception that we'll get to in the next slide. But just some examples here of the naming of carboxylic acids. So this one is propanoic. Okay, propane, we changed the suffix, we got rid of the E and we added the oic acid, and it's propane because it's got 3 carbons in it, 1, 2, 3. Okay, this one shows you how to deal with a substituent. So we number them from the position of the carbonyl. So that's carbon 1, 2, 3, 4. And on carbon 4, we've got that methyl substituent. So 4-methyl, and it's a total of 5 carbons. So pentanoic acid. Okay. And in this one, again, there's so many variations. I don't expect you to know every little detail, but this just shows you an example how to deal with more than one carboxylic acid group, like on the ends here. Okay, so 1 in position 1 and position 8. So it's dioic acid. I guess that's the main point of this particular example, is to show you how to deal with a situation where you have more than one carboxylic acid functional group. You say dioic acid. This is the situation where the carbon in the carboxylic acid functional group is not numbered as 1. That's the situation when it's an offshoot of a ring. So compounds with COOH bonded to a ring are named using the suffix carboxylic acid, right? And the COOH is not numbered in this situation. And also, if the carboxylic acid is considered a substituent, then you would refer to that COOH group as a carboxyl group. I'm just trying to introduce you to some of the vocabulary here. So many times they'll say, oh, well, the carboxyl group is going to do this, or the carboxyl group is responsible for that. What they're talking about is that carboxylic acid functional group, thinking of it as a substituent. So just get comfortable with the vocabulary a little bit. Okay, so again, here's just a couple examples on how to deal with the carboxylic acid functional group as a substituent on a ring. All right, so this one, for example, it's a 6-membered ring, so it's a cyclohexane, and it's got a carboxylic acid on it. It's not numbered. It's not, one of the numbered carbons. But we know that the carbon number 1, with a ring, if the number is not given for the substituent, that means it's on carbon number 1. So this carboxylic acid group is on carbon number 1. And then if you look over here on carbon number 4, we've got this OH group, which when you're naming that as a substituent, it's called hydroxy. And we throw the trans in there because this ring, they're on opposite faces. The hydrogens are on opposite faces, or the two functional groups are on opposite faces. So trans 4-hydroxy cyclohexane carboxylic acid. Okay, and over here, 1-cyclopentene carboxylic acid. The 1, it's not because of the carboxylic acid. You're specifying position 1 here to talk about the point of the position of the double bond, the alkene functional group. All right, so also just be aware, this table I did not put in your handout because it's too much, but carboxylic acids have been studied and characterized for a long time, before scientists even knew much about organic molecules. And so because of that, there are a lot of carboxylic acids that have common names. They're not referred to by their IUPAC name. So many carboxylic acids are known by a common name. And again, you may recognize some of these from your biology classes, like lactic acid down here, okay? Malonic acid, oxalic acid. These show up in like the citric acid cycle. Oxaloacetic acid. So if you remember your Krebs cycle, your citric acid cycle, the glycolysis, different processes like that, these names should look familiar. Okay, so let's do a couple examples. So we want to give the IUPAC names for the following compounds. All right, so we'll look at the structure, see if we can come up with some names here. So first of all, as I said, we're going to number them where the carbon that's on the carbonyl is going to be 1, and then the longest chain I've got 2, 3, 4. Okay, so the parent name is going to be butanoic acid. But in this case, I've got this methyl group at position 3. So 3-methyl butanoic acid. Okay. And down here, again, I got the cyclopentane ring. Okay, so that's kind of the root. So I'll go ahead and write that down, cyclopentane. All right, and I've got 2 carboxylic acids here. Okay, so I'm going to do the, and also both of these are substituents on the ring. Okay, so cyclopentane, and then the way I would use the correct, naming conventions is I would go dicarboxylic acid. So some of these names obviously get pretty long. Okay, but in this case, we do need to indicate the positions. Obviously, one of them is at position 1, but then if we minimize the number, keep the numbers as low as possible, then the other one's going to be at position 3. So 1, 3. Okay. And then a dash. That one other thing I forgot to put on here. So I'll kind of put it out. I'll do a little caret here. So these are on the same side, right? Coming out of the screen, coming out of the screen. So this is cis-13-cyclopentane dicarboxylic acid. 3-methyl butanoic acid. Yep. And then cis-1,3-cyclopentane dicarboxylic acid. All right. And just to reiterate, my expectation when it comes to naming, just recognition knowledge, be able to pick out the correct name from a selection, or given a name, pick out the correct structure from a selection. Okay, so one more thing about naming carboxylic acids before we move on, and that is we're going to learn in just a slide or two that hydrogen that's part of the functional group is acidic. And so if you remove it, then the ion that you've created, that negative ion, that anion, is called an 8. The suffix changes. It's no longer an oic acid, it's an 8. So when the carbic acid has been stripped of its acidic hydrogen, the resulting anion is renamed with the 8 suffix instead of the oic acid. And so you see the example here. Before, we would call this acetic acid. That's the common name. That's not the IUPAC name. That's the common name. But if we take off that hydrogen, then it becomes acetate, right? Okay. So we'll move on from naming to talk a little bit about the structure and properties of carboxylic acids. So the carbon that's, sort of forms the base of the functional group is sp2 hybridized, right? Which means that the atoms it's connected to are all in the same plane. It's a trigonal planar geometry, and it has bond angles of about 120 degrees. Okay. So something else that's important about carboxylic acids is that they can accept and donate hydrogen bonds. They meet the requirements. They've got that oxygen-hydrogen covalent bond, which remember that the reason why that's so important is because it gives you that highly polarized bond where this is the partial negative and the hydrogen is partial positive, partial negative, partial positive. Okay. And in carboxylic acids, it's energetically favorable for them to actually form these dimers where they align themselves to where they're, one is forming a hydrogen bond with another. It's donating one and it's accepting one. Okay, because the lone pairs on these oxygens can serve as electron or hydrogen bond acceptors. Okay. All right, and so one of the resulting, properties that changes or is affected by this is the boiling point. And you could also say the melting point, I guess, because a lot of carboxylic acids are solid at room temperature. So it causes higher boiling points than corresponding alcohols, because alcohols also were a functional group that could donate and accept hydrogen bonds. But these have even higher boiling points than similar alcohols. So one of the other properties that we talk about sometimes is solubility. And small carboxylic acids are relatively soluble in water, and it stays that way until you get to about 6 carbons. If your carboxylic acid has about 6 carbons or more, then we would say it's only slightly soluble in water. So carboxylic acids with more than 6 carbons are only slightly soluble in water. But the other interesting thing is, and we've actually have some practice with this that I'll talk about in just a minute, but if you create that negative ion by stripping away the hydrogen, that acidic hydrogen, and you make a salt with that, so you got a positive ion and a negative ion, those are water soluble. So the conjugate base salts of carboxylic acids are water soluble. And so, for example, if you have something that's insoluble, but then you react it with a base to something that pulls away that acidic hydrogen, and you form this salt where you got the carboxylate, okay, and then the counter ion that's so in this case sodium +1, then that's going to be water soluble because it's an ionic compound, like NaCl, which we know is very water soluble. Most ionic compounds are very water soluble. So if I take the carboxylic acid and I strip away that H+ to make it an ionic compound, a salt, then it becomes much more water soluble. Okay, and this is actually, like I said, something you have practice with in that lab that we did several weeks ago, and you wrote your formal lab report on, where we were trying to isolate each component of a mixture, that panacetin lab. Okay, hopefully it's ringing bells. Remember that you dissolved the mixture in a 10% solution of sodium bicarbonate. That was a base that stripped away this hydrogen and made the sodium salt of aspirin, which went into the water layer, was dissolved in the water layer, and you isolated that later by reprotonating that carboxylate, making it once again a carboxylic acid, and precipitate it out. So this type of chemistry is utilized all the time to sort of make the molecule move to whatever layer you want it to dissolve in. If you want it to dissolve in water, you strip away the acidic hydrogen and it will dissolve in water. If you want it to precipitate out of the water, you treat it with an acid, it grabs hold of that hydrogen and is no longer soluble in water or very soluble in water and precipitates out. Okay. So we've already kind of established this, and the name kind of gives it away, that carboxylic acids are acidic. They're weak acids. All right. So when you put carboxylic acids in water, when you mix the two together, you create some hydronium ions. Remember, that's the telltale reaction for acids. They create hydronium ions. Okay, now they are weak acids. Their Ka, which is the acid constant, the ionization constant, is less than 1. It's significantly less than 1. It's in the range of 10 to the -4 to 10 to the -5 for typical carboxylic acids. Now, remember, we've been talking more and more about pKa's lately, right? So a Ka is different than a pKa. The pKa, remember, is equal to the negative log of the Ka. And so if we were to think about the pKa's of these, it would be anywhere between 4 to 5, because the negative log of 10 to the -4 is 4, the negative log of 10 to the -5 is 5. So the pKa's of carboxylic acids tend to be in that range of 4 to 5. All right. And every hydrogen at some point will come off as H+, but we don't typically think of things as being acidic unless that happens in water, right? And we've already learned that alcohols, when we talked about alcohols a couple weeks ago, they have about the same acidity as water. They are like a derivative of water. Instead of HOH, it's ROH. So they have pKa's that are similar to water. But when you throw that alcohol group on a benzene ring, because of resonance stabilization, it becomes a little bit more acidic. That has a lower pKa. Remember, that's the trend. The lower the lower the pKa, the stronger the acid. Okay. So phenol, which is an alcohol on a benzene ring, is more acidic than a typical alcohol. Well, carboxylic acids are even stronger acids. They have lower pKa's in that range of 4 to 5. Acetic acid has a pKa of 4.76. Okay, and then something like a strong acid, just for comparison, has a really low, even negative pKa. Okay. Now, with carboxylic acids, there are also inductive effects. Now, if you don't remember what that means atoms that are connected, but maybe farther away, due to their properties, particularly their electronegativity, can affect the acidity. So inductive effects, the carboxylic acids become stronger when electronegative atoms are present as substituents. So they become stronger when electronegative atoms are present as substituents. And so the next chart there, or the diagram that you have there in your notes, shows this. So again, our baseline for this example is going to be acetic acid, which is over here on the left. It has a pKa of 4.72. Well, if you replace one of the hydrogens on that methyl group with a chlorine, which is more electronegative, then the pKa goes lower, 2.85. So it becomes stronger as an acid. So this hydrogen becomes more acidic. You do it again. You replace another hydrogen with another chlorine. It becomes even a stronger acid. So this hydrogen becomes more acidic. And you do it 3 times, you get trichloroacetic acid. So all 3 of those hydrogens have been replaced with chlorines, and you get a pKa of less than 1. So a fairly strong acid. Okay. And if you do this with fluorines instead of chlorines, because fluorine is even more electronegative, then the pKa actually goes a little bit negative. It becomes like a negative 0.2. So that's the inductive effect. So these, remember the reason why is because these electronegative elements, these chlorines, their electronegativity kind of sucks electron density out of this OH bond. It pulls electron density out of that OH bond, making it easier to pop that H off as an H+. It kind of weakens that bond because it through the inductive effect, it's electronegative, right? So it pulls electrons out of the rest of that molecule towards itself. Okay. Now, we see the same trend actually in aromatic carboxylic acids. So these are carboxylic acids on a benzene ring. So the same trend is observed in aromatic carboxylic acids. Okay, and so again, a couple weeks ago, we talked about substituted benzenes. And we said that some substituents on benzene are considered to be electron withdrawing. And that affected a couple things. It affected how easy it is for that benzene to add another substituent. We call that activating or deactivating. But it also directed the placement of new substituents, whether it went ortho and para or meta. Remember all that? So if the substituent on the benzene is electron withdrawing, it makes that carboxylic acid a stronger acid. And just the opposite, if that substituent is what we called electron donating, it makes the carboxylic acid a weaker acid. So here's just some examples. So again, our baseline in this case is going to be the unsubstituted carboxylic acid, so benzoic acid. It's got a pKa of 4.19. Okay, well, let's look at nitrobenzene first. So nitro, if you remember, was an electron withdrawing substituent. It kind of sucks electron density out of the ring through resonance forms. So it can participate in the resonance structures along with the benzene ring. So that effectively pulls electron density out of the benzene ring. Well, what that's going to do is that's going to stabilize your carboxylate anion. And it also, again, you could think of it as weakening that OH bond to make this a little bit more acidic of a hydrogen. So that's why the pKa is lower, 3.41, stronger acid. Well, let's go to the other side. So we said that the methoxy group, the CH3O, okay, this is like like an ether, right? ROR. So that kind of a group was electron donating. It pumped electrons into the ring. Well, that's going to, eventually kind of through inductive effect and through resonance effects find its way into that OH bond, strengthening that OH bond, making it a little bit harder to pop that hydrogen off as an H+. And so it's a weaker acid. And it's reflected in the fact that the pKa is a little higher. So it went from 4.19 up to 4.46. So electron donating groups make it a weaker acid. Electron withdrawing groups make it a stronger acid. Okay, so let's do a little practice here. So we're going to rank these 3 according to their, acidity. So rank the following compounds in order of increasing acidity without using the table of pKa data. All right. So once again, let me just draw a little bit on here. I know you don't have a whole lot of room on your handout, but let me kind of draw. So the benzoic, let's do it right here, I think. So I'm going to draw a benzene ring. And on one side, I'm going to put the carboxylic acid, so C double bond O, OH. Okay, on the other side, I'm going to put X. And so for benzoic acid, that X just equals a hydrogen. And for the para-methylbenzoic acid, that X equals a CH3 group, a methyl group. And for parachlorobenzoic acid, the X just equals a chlorine, all right? So we need to think about, well, you know, and again, so this is going to be like our baseline. This is our standard, our baseline. So I know that this one is going to be, you know, we're going to say that the benzoic acid is going to be the middle. It's going to be in the middle. And I'm going to label one of them as stronger and one of them as weaker acids. So which is which? Well, the methyl, remember, is an electron. It's a donor. It's an electron donor. Okay. So we said that means it's going to be, it's going to weaken this acid. So it's going to be the weaker of the three. And the chloro, remember from our discussion about, you know, substituents on a benzene ring, it was ortho and para directing, but it was considered deactivating. It's like electron withdrawing. So this was a deactivator. So this is, you know, an electron withdrawing. If I can spell, I'll just put electron withdrawal. Okay. And because it's electronegative, through the inductive effect, it's going to pull electron density out of that ring. And so that means it's going to be a stronger acid. So of the three, methyl benzoic acid is the weakest, benzoic acid is in the middle, and then the parachlorobenzoic acid is going to be the strongest. Okay, so we talked about the properties of carboxylic acids. Let's talk about how to prepare them, how to make them. So one way to do it is, believe it or not, you just start with a alkyl benzene. Okay, and you oxidize it with something that's pretty strong as an oxidizing agent like potassium permanganate or sodium dichromate. So gives you a substituted benzoic acid. Oxidation of a substituted alkyl benzene with potassium permanganate or sodium dichromate gives a substituted benzoic acid. But the one limit to this is that it doesn't work with tertiary alkyl substituents. Okay, and we don't even go through the mechanism on how this happens. Just I want you to, you know, make a flashcard or whatever to know that it does happen. So this methyl group, this alkyl substituent on a benzene, becomes a carboxylic acid. And it really doesn't even matter what it is. It could be, you know, a 3-carbon chain, it could be a 2-carbon chain, but you're still going to end up with a benzoic acid. Okay, because the oxidizing agent kind of cleaves that carbon from the rest of the alkyl chain to make the benzoic acid. Okay, now this one we've seen before. So we've talked about alcohols and we've talked about aldehydes and we talked about oxidizing those. So you've seen this before. You can prepare a carboxylic acid by oxidizing a primary alcohol or an aldehyde. So we've got an example of each one. So 4-methyl-1-pentanol, it's a primary alcohol. We just mix it together with, in this case, chromium-6 oxide in acidic conditions, and you get the 4-methylpentanoic acid. So the alcohol group has become the carboxylic acid group. Or down below, we can start with a aldehyde, in this case, hexanal. And same thing, you just mix it together with a strong oxidizing agent in the acidic conditions, and it converts the aldehyde into a carboxylic acid. Okay, well, here's another way to do it. It's called carboxylation of a Grignard reagent. Okay, so hopefully you remember what a Grignard reagent is. That's something you can make with a alkyl halide, but you'll get you'll have your memory refreshed here in just a second. But all you do is you take that Grignard reagent and then you react it with carbon dioxide, dry ice. I remember doing this one actually in my undergrad organic chem lab. Again, back when dinosaurs roamed the earth. But so I don't know. We're not going to do it. You might do it in organic 2 if you had to take organic 2, but this reaction typically works really well. Okay, so then after you react the Grignard reagent with carbon dioxide, then you just treat the solution with a strong acid, and you end up with the carboxylic acid. So there's 2 steps, which is demonstrated in this diagram right here. So for example, if you have phenyl magnesium bromide, remember that's your Grignard reagent, right? You start, in this case, we started with the phenyl bromide or the bromobenzene, I guess, and then we reacted it with magnesium to create the Grignard reagent. Okay, we talked about that way back when we were talking about alkyl halides. And remember what that does. That turns this carbon that's connected to the magnesium, it turns it into something like a carbanion. It's got like the partial negative charge. So it's like a nucleophile. So that then is going to attack this carbon, which is behaving like an electrophile. Okay. And it adds to it. So you add that group to the carbon in the CO2. All right. And then, you in this case, we've got an ionic compound. You got the anion, you got your cation. Well, we can just treat that with an acid, and it puts a hydrogen on this oxygen, right? So you get your benzoic acid out of that. Okay, so carboxylation of Grignard reagents. Grignard reagents react with CO2, and then the addition of a strong acid in a separate step gives the carboxylic acid. Okay. All right, so let me do an example of this. So here, how is the following carboxylic acid prepared? And we got condensed structures written here. So I'm going to draw this out to do the line skeletal structures. So in this case, what we're starting with, I'll draw this molecule first. So it's like a T-butyl chloride. So the carbon that's connected to the chlorine is that carbon right there in the middle, which has 3 methyl groups also attached to it. So they're methyl group, methyl group, methyl group. Okay. So remember that the first thing I need to do is turn this into a Grignard reagent. And the way you do that, first of all, is you mix it together with magnesium, solid magnesium in ether. Okay. And that's going to create the Grignard reagent, which becomes like that. So the magnesium kind of just inserts itself between the carbon and the chlorine. Okay, so there's your Grignard reagent. Okay, so then we said that, well, let's just react that with, carbon dioxide. Okay, so there's going to be my nucleophile. It's going to attack that. Okay, and then that's going to move down there. And so then the product of that is going to be your T-butyl. And so now it's got another carbon. It's got the C double bond O. That's that C double bond O right there. And then I've got an O with a negative, because this pair of electrons moved on to the oxygen to give us the formal negative charge on the oxygen. And then I've got my magnesium bromide left over as the positive charge. That's like my cation, the counter ion. Okay, but then all I need to do is just treat that with some acid, H3O plus. All right, and then I get the T-butyl, and then the C double bond O, and then the OH. Okay, which again, this is just the skeletal structure of what is written in a condensed way here. Yes, that is true. So, I guess it's kind of good that I make that mistake, because remember that these Grignard reagents can be made with chlorines or bromine. Okay. In this case, it was chlorine. I should have caught that. Thank you.